Hello everyone, I'm Mohammad Sedghpour, a former PhD student at Umeå University in Sweden. I'm really excited today because I'm going to present you HydraGen, a microservice benchmark generator. This work is a joint work between Umeå University and Ericsson Research in Sweden. Before we deep dive into our study, let's take a look at the definition of microservices. Microservice is an architectural style that structures an application as a collection of distributed services with multiple instances that function as cohesive and independent processes interacting via messages. These services are highly maintainable and testable, they are loosely coupled, they are independently deployable, and most of the time they are owned by a small team. The combination of microservices and advancements in software development practices, namely DevOps, has enabled us to build more scalable applications while deploying them to production rather super quick. This actually makes them exciting for researchers like me and my colleagues. While microservices brought many benefits, but they also introduced some operational challenges, and a possible research direction could be performing comprehensive and fine-grained performance sensitivity analysis. For instance, we may need to study the impact of communication patterns, topological architectures, or resource usage characteristics on our proposed methods in our research. Currently, to evaluate our tools, most of us use some sample applications. As we all know, there are tens of such sample applications, most of which represent typical microservice architecture and mimic online services widely used in domains such as e-commerce. To get a feeling about existing applications, in this table we can see a series of existing benchmarks in each column. And by simply looking at the number of microservices row, we can see that these applications have very limited and fixed complexity in terms of size and topology. But in reality, the number of microservices and the way that they are talking to each other could be more complex. And they might be thousands of services with multiple instances that are updating rather quickly with existence of CI/CD pipelines that we are all familiar with. To this end, this paper aims to tackle this limitation. The primary objective of this paper is to be able to study the impact of topological architectures, resource usage characteristics, and communication patterns. Secondly, we aim to enable studies of more complex microservice architectures and scenarios. And finally, enable gaining new research insights by showing a sample traffic management study that we already have done previously. So, in this joint effort between Umeå University and Ericsson Research, we have implemented an open source HydraGen, which is a microservice benchmark generator. It can emulate more realistic and customizable microservice-based applications. HydraGen enables us to generate and customize any architecture we may need for our research. For instance, we can modify workload placement and scaling. We can limit the required resources for each service. We are able to generate a fancy and unique architectures with different computational and network complexity for each particular service. You can have access to our repo by simply scanning this QR code. Feel free to scan and take a look at our code. Here is how we implemented HydraGen. HydraGen actually consists of two main modules, the application generator module and the application emulator module. The application generation module implemented in Golang can be used to generate a microservice-based application with a specific topology and complexity. The tool supports two different modes, preset and random. In preset mode, the user can precisely describe the configuration parameters of the application they want to emulate as a JSON format and as input, and the generator, on the other hand, outputs a set of Kubernetes manifest in YAML format. In random mode, on the other hand, the tool automatically generates an application with random acyclic topology and random complexity based on a smaller set of constraints given by the user. And in this random mode, the tool generates both the JSON description file and a set of YAML Kubernetes manifest. So Let's move on to application emulator. It emulates the execution of all microservices that are part of the application. It is implemented in Python right now, but there is a work in progress to re-implement it in Golang. We will discuss that later. It can run as either an HTTP server or a gRPC server. It also implements the supported resource storage source for both CPU and network. To get a basic feeling about HydraGen, in this slide you can see a limited overview of how we can design our application in JSON as input of application generator module. And in the bottom also, you can see that we can generate various architecture with different complexities. Of course, the large architectures are not shown due to the limited space that we have in this slide. To evaluate our tool, we employ two different scenarios. First, we replicate some characteristics of an existing benchmark. These characteristics include maximum supported throughput, let's call it capacity, and the second is time needed for each request to be processed by the CPU, which is called CPU time per request. And finally, the third one is latency, which is 95th percentile of the response time associated with the requests. The second scenario, on the other hand, is to study the impact of architecture on the performance of adaptive circuit breaking from a previous paper to highlight that it can get new insights. So now let's move on to the first phase. So we chose to replicate bookinfo, which consists of 4 microservices that are developed in different languages. As shown here, reviews service has 3 versions, v1, v2, and v3, out of which, for simplicity, we only include v1 in our experiments. And then the microservices are arranged in 2 main service chains, and requests can be directed through up to 3 microservice tiers. In our study, we deployed this real bookinfo application and our emulated application on a Kubernetes cluster while generating different traffic scenarios. And also we measured the capacity, CPU time per request, and the latency for each request in each service for just having an understanding of how we deployed all of these things. You can read the section testbed setup in our paper. Let's see how different the real bookinfo and the emulated application behave. In the left chart, you can see the distribution of maximum throughput for each service in both applications. This chart shows that the emulated application has almost the same capacity as the real application. On the other hand, in the right chart, we can see the time needed for each request to be processed by the CPU for each service in both applications. As shown here, the rating and the review service in real application have really low CPU time per request in comparison to emulated ones. The main reason for that is that they are simple services that are implemented in Java and JavaScript that are more efficient than Python that we chose in our tool. Actually, that is why we decided to implement the application emulator in Go, so that we can fix this issue, and it is actually an ongoing process that we are tackling. Now it's time to talk about second phase. In a previous paper, we aimed to auto-tune circuit breaker to maintain the tail response time while maximizing the throughput. So we proposed a controller for such objective. We have tested this controller in various scenarios as shown in the right chart for a single service application actually. In this way, we were able to evaluate the performance of this controller. For more information about the controller and the experiments, you can just take a look at the paper that is here in the footnote. But how should we evaluate its performance directly for a multi-tier application? I mean, as all of the existing benchmarks have different complexities for different microservices, it might impact our results. And we want to isolate that impact. That is why we generated 3 applications using HydraGen. These applications have different number of tiers in their architectures, but with the same complexity, to only study the performance of our controller. In this slide, we can see the distribution of both response times and throughput of each application from an outside client perspective when either one of the adaptive circuit breaking or static circuit breaking is enforced. The first row shows the response times and the second row shows the throughput. Each column also indicates different application architectures. The blue boxes shows the result of adaptive circuit breaking, and the orange ones indicates the static circuit breaker configuration. The results show that the adaptive method can stabilize the response time while maximizing the throughput. But more importantly, we were not able to perform such a study without HydraGen and with the existing benchmarks. To conclude, we learned that the HydraGen enables us to explore new insights by providing dynamic capabilities that we can manage ourselves and are not offered by the other existing statics benchmarks. We were able to emulate any architecture needed for our studies, including existing ones, and thus we could directly assess how architecture characteristics impacted our controllers. And also we believe that distributed system researchers and cloud researchers can improve the reproducibility of their research by using HydraGen. Thank you very much. Please feel free to scan this QR code to access HydraGen repo, and also feel free to contact us if you need any help for using HydraGen. Thank you.